continue the discussion on group theory. Last class we were discussing about representations. There are two types: reducible representation and then irreducible representation. In that, how we go from reducible form of representation to irreducible by similarity transformation. So if you can reduce it further, then the dimension of the matrix reduces. It could end up with 1 dimension or 2 dimension or 3 dimension. This is done by similarity transformation. So each one is we defined as a class of matrix. So basically, the given matrix is block diagonalized by similarity transformation. In a matrix form, I have just written a matrix here. I hope it is visible. Let me close this. Yourself. Okay. So I hope it is visible now. So I have written by 6 by 6 diagonal matrix or block diagonalized matrix, and this is called representation. So once you block diagonalize it by similar transformation, then you can see this is 2 by 2 matrix. This. So I can write separately A, B, C, D, and then PQ. That gives rise to P prime, Q prime. So what it means is this P and Q are the basis, and this is the representation. So A, B, C, D for 2 by 2 matrix is a representation, and P and Q are bases. So bases, I was telling in last class or earlier, bases could be anything. The vectors, it could be bond between two atoms. It could be Cartesian coordinates. So like that we can take. Those are the bases. So this is basis, and this is a representation. So it's a 2 by 2. So it's a 2-dimensional in character. Similarly, E can be. We can write E is a representation. R is a basis, and it will give the new form R prime. And here, this is the matrix FGH. So I can write again FGH IJK element is a representation, and basis is this one STU. So this is the basis. Okay, so if you take the basis, multiply with the representation, then it will give you a new matrix. The solution it will get. So this is in S time, V time, T time, U time. Okay, so it will give 3 by 1 matrix. So what we have done is basically a complex matrix by block diagonalization in the form of similar transformation. We have made it into a block diagonal matrix. You can see all the diagonal elements are filled up, and you can separately multiply it to get the solution. What I'm saying is this is the basis and this is the representation. Okay, last class we were talking about reducible representation, and even if you take this matrix, block diagonalize it, then you can make this one 0, this one 0, and only these two elements will remain. So that one can reduce further. So that one can reduce a 2 by 2 matrix to 1 by 1 matrix. Then that process is called as we go to the irreducible representation. If you cannot reduce further, it just remains as such, like 2 by 2, this one remains as such, 3 by 3, then we call it as irreducible representation. With this background, people use notations, what is called as for representations. Different people use different notation. Yes. And initially it was used as something like gamma. A symbol is used, something like this. It's called as Betz notation. Okay. So we write gamma 1, gamma 2, gamma 3 like that. I'll explain with an example. Let's take water molecule. me go with the notes. What is the... Okay, so this is y, this is z, and this is x form. Okay, the coordinates are defined as x is towards right, towards top is z, and x is coming out of the board. Okay, so you know this is C2D. Let's write the matrix for these three vectors. So these three Cartesian coordinates we can write. So if you, this one it will be 1 0 0 0 1 0 0 0 1. So this is simple. Okay, and I write for C2 of z. So C2 of z is I'm placing here the Cartesian coordinates z is towards it, so I'm going to rotate 180 degrees. So these states to be interchanged. So to perform the various operations, the atom, what x is going to, so if I rotate it by C2, this x will go to the minus x. It become minus x. So I can write -1 here, and then y is going to become -y. Okay. So I write -1 0 0 0 +1. So z is not going to change anything. Z will remain plus g itself, okay, by rotation. So this is for C2. And I'll apply sigma v prime. If I cut the molecule into half along xz plane. So xz plane, I'm just placing a mirror across this molecule, and then let's see what happens. So if I cut the molecule into half, so x is going to happen nothing. So x will remain as x, and y will come to -y. So I write -1 0, and then z again is going to remain as such. Z will be positive z only. There is no change of position or there is no change of sign. So this is sigma prime. I write to sigma v double prime, which is placing on the yz plane. So let's place it on yz plane. If I place it on yz plane, the x will become -x. 0, y will become same, no change. Z also going to be same. Okay, so now I got the matrix elements. So what I'm going to do is write in a table form. Okay, with this notation. C2V which is this one, xz. And sigma v double prime yz. So what I'm going to do is I write various gammas. So let's say gamma 1. I choose the first row of every element. So this is 1 for C2, 1 for E, -1 for C2, and 1 for sigma v prime, and sigma v double prime is yz. So visible. This row visible? No, it's not visible. I make it even smaller. Start from here. So I take x-axis. This is x, right? This row is a correspond to x. So I write for various symmetry operations. So this is for x. So for if you perform x-axis and then perform e, it's not going to change. So it's a 1. That's what we got in the matrix form. Perform C2. then it goes to -1. So that's why it's -1 here. I'm writing it here. And then sigma v prime, you can see it is again 1, positive 1. And then sigma v double prime is -1. That's why I've written here. So this is for the next column we write for x-axis. This is the representation 1, -1, 1, and -1 for these symmetry operations. Now let's go to the gamma 2. It's a y-axis we can take. So if you take this y-axis, its matrix elements are for E it is 1, and for C2Z plane, C2Z rotational axis, again it is -1, and then sigma V plane, again it's -1, sigma V double plane is 1. So this is positive 1. So this is for Y. Okay, so that is the third row also, Z-axis. So we call it as gamma 3. And then we can write that. So this is again 1 here. And see this is 1 here. For E, for C2Z, it is again 1 here. It's positive 1. And sigma V prime, it is again 1 here. Positive 1. And last one is also 1. So all 4 are 1. Okay, so this axis is Z. So if you keep monitoring the Z-axis, if some orbital is present and perform, place it on Z-axis, if you perform these operations, then it is always going to be symmetry, all positive, 1, 1, 1, 1. Okay, so that's the message. So we can take in water molecule, we can take px orbital and see what happens. Let me write for that. Say px orbital of water. Let's perform all the operations for px water. So E of px performs going to be remain px. So px is basically here, right? So px is you can plot it. So something like this: plus is towards you, minus is backside. So it's somewhere here. Okay, p orbital is towards coming towards us. Positive part, the negative lobe is behind the pole. So if you perform this operation, E of px is going to be px, C2 of z with px orbital. If you consider the orbital, then let's see the symmetry element. So this is 1 time of px. Okay, so plus 1 of px. Similarly, if you perform C2z of px, so px orbital is somewhere here. You perform C2z, it just goes other way, right? So it is so minus 1 of px. So it just changes its sign and gives back the px. And third is sigma v prime, which is cutting the board, so cutting the molecule sigma z. So molecule is px orbital like this, and then you are placing a mirror, cutting the p orbital into half exactly. So that shape is not going to change. So it's again plus 1 of px and sigma v double prime yz. So if you're following px orbital, sigma yz place on the plane of the board, so you will cut the plus lobe and negative lobe into half, so that becomes minus 1 of px. Okay, so now you can see the symbols, numbers 1, -1, 1, -1. Okay, that's what we have written it here. 1, -1, 1, -1. So for the x-axis or x direction, this is going to be the matrix elements, or we can say these are the characters of the representation. Okay, so similarly, if you take the z orbital and perform these operations, you will end up with the symmetric representation 1, 1, 1, 1. So if pz orbital will be, it's not going to change anything. If you take pz orbital, that's why it's all highly symmetric. So you get z. To try for py, so py is this way, right? So y is this. So plus minus. So if you try this, then you end up with this symmetric, this characters 1, -1, -1, 1. So these are the representations in the matrix I was telling. No, in the matrix form you can write. So that these are the representations, and these are the bases. X, Y, Z are the bases. It could be Px, Py, Pz orbital, or just Cartesian coordinates X, Y, Z. So these are the bases, and these are the representation. And since these are a 1, -1, you cannot go for below that. So these are called one-dimensional representations. If it is two-dimensional, no, it will be number 2. Number 2 will be there. Okay. If it is three-dimensional representation, it will be 3. So we just started building this. So this is kind of called as a character table. Okay, with having a point group, symmetry, operations, and then these are the various characters, and these are bases. Okay, so and these are the representations. Now we have not decided whether that is a reducible or irreducible, but these are gamma. The symbol beta used is gamma. So this is gamma 1, gamma 2, gamma 3. So these are representations. So if you start writing in this form, these are called as a character table. One can write on character table various molecules. Maybe I'll take, since we're talking about character table, fine, we'll go to next that. So this is for water molecule, right? We'll take it for cis butadiene, and let's see what happens. You know, cis butadiene is this much, right? So we take the pi orbitals of cis butadiene. So basically it is C4H4. So this is basically to visualize it. So this bond is coming towards you, you can say, and so basically this is this plate is placed something like this. Okay, this framework C4 H4 framework or something like this, and these orbitals are above and below. So one is above, and then others are all other way. So these are negatives. Okay, so you can think these two carbons are coming towards you, and this carbon is on the board. Okay, so something like this, and then your 4 lobes are present. So if you apply a C2B again, how the matrix form will look like for E? Can anyone tell me what will the matrix form for cis butadiene? Considering the axis, like axis we have to define. So let's define this as either way. Anyway, you can define as you wish, but this is x, this is y, and say this is z. Okay, so now we have just changed the axis, but yeah. So for E, anybody can answer what will be the matrix form for cis butadiene for symmetry element E? You guys are online?
Yes.
Yes, okay. Yes, tell me what will the symmetry, matrix form of cis butadiene E?
400, as all are same at their place.
So it will be like this. Okay, so this is although we are saying XYZ, I'm interested in the lobes, 4 lobes. So I call this one as phi 1. This is phi 2. This is phi 3, phi 4. So I'm interested in how the lobes are changing with all the symmetry operations. So this is 4 by 4 matrix, and this is not going to change. So this for E it is 4 by 4 matrix. All diagonal elements are 1. Now I'm going to rotate the C2 along y-axis or z-axis. C2 we rotate. How do you rotate? Okay, so you can C2Z. So we rotate to this way, right? No, since we have placed the molecule something like this, so we have to rotate along z-axis. Okay, C2Z. And we are rotating it, so then the matrix form, if you rotate it 180 degrees, so phi 1 will become phi 4. So that means this will occupy phi 4 with a negative 1. Phi 1 will become phi 4. And if you try with phi 2 will become phi 3. It will be here, but it will become phi 3. And this goes to inverted. So minus 1, 0. And then it will be interchanging. So phi 3 will become phi 2 with the negative sign, 0, 0. And again, phi 1 has gone here, phi 4 will come here. So 1 minus 0, 0. So C2 of Z will look like this. You can see the orbital, phi 1 has gone to the phi 4. While going it, since we are rotating now 180 degrees, so pi lobe, this P lobe, which is positive, has become negative when it goes to phi 4. That's why you have put phi minus 1 here. So same thing for phi 2, phi 3, and phi 4. What about sigma V? Sigma V. So we cut the molecule, right? One is, you can say one is. So if you YZ, you cut YZ, what happens? How the matrix will look like? Okay, so this is one is YZ, other is XY. XY or XZ. XZ. So we have considered the molecule as something like this, no? So we are going to cut the molecule into half. So if you cut it, so all the lobes will be cut into 2. So, but the atoms will be placed there itself. So this is 1. Maybe you can say first let's try with YZ itself. So very confused. We just start with the YZ. So YZ is cutting across YZ. So what happens? YZ is atoms will interchange, but positive sign. Zero plus 1, 0, 0 plus 1, 0, 0, 0. So basically, one plane is cutting the molecule. So when you do that, phi 1 will be replaced by phi 4. So that's all. Instead of phi 1, it has gone to phi 4, and phi 2 has become phi 3. So here phi 2 has become phi 3. Again, phi 3 has become phi 2, and this one, phi 4 has become phi 1. So, but there is no change of sign. Okay, so all positive lobes will fall on the positive lobes. So there is no change. That's why diagonal elements all are positive. This is sigma V prime. Sigma V double prime you can write. So this is sigma V double prime is XY plane. No, is it XY? YZ is done. So XZ plane. So XZ plane. Cut. You're cutting XZ plane, the molecule into 2. The lobes are all cut into half. So location is the same, but charges are all changed. 0, 0, minus 1, 0, 0. 0, 0, 0, minus 1. So this is what happens. So atom position or the lobes position is not changing. Cut the molecule into, the lobes are all cut into half. So positive will become negative, just inverted. So these are all phi 2 will become minus phi 2, phi 3 will become minus phi 3, phi 4 will become minus phi 4. That's what we have written here. On E, just the sign has been changed. So we write in terms of matrix elements. Now this can be written as, so these are all square matrix. So we sum up the diagonal elements. Okay, these are the characters of a matrix. If you find the trace, so it is for E it is 4. So it is 4, trace is 4 here, and C2 Z it is, if you sum it up, trace is 0, and you sum up sigma V double prime or sigma V prime, again it is 0. The trace of the matrix, here it is minus 4.
Excuse me, sir.
Okay, so we are considered sigma C2V. You can write the basis as 4 for C2 0, for sigma V prime 0, and sigma V double prime 4. So based on a matrix, we wrote it and then we are summing it up, right? So that is, we have got 4, 0, 0, minus 4. So if you write like this, it is called as reducible representation. So because the dimension is very high, so we can reduce it further. So this is called as reducible representation. So 4, 0, 0, minus 4 we got, right? So that's a reducible representation. Okay, so we are just interchanging this. It could be what? So sigma V prime YZ. YZ we are calling as double prime here. So we got this one 0. I'm sorry, then it should be like this. This should be minus 4 and this should be 0. Okay, so this is sigma V prime. So sigma V prime is XZ. So I just call this as XZ, and this is double XZ. And YZ is just remember sigma V of YZ is 0. Sigma V of YZ is 0, and sigma V of XZ is minus 4. So this is minus 4. So it doesn't matter even if you interchange, provided you just write the corresponding axis, the Cartesian coordinates, then it should be fine. So this is a reducible representation. We got something like this. If you go by the matrix element also, by the row also you can say yes, yes.
Sir, so we formed this C2B table for H2O molecule, and now we are comparing with the reducible representation of cis-butadiene.
Yes.
So shouldn't we do it for water? Find the reducible representation of water molecule also?
Yeah, we can do it for water molecule also. We can do it. So here what?
So why we are?
If you remember, for water molecule, we wrote 3 by 3 matrix, right?
Yes, sir. But sir, I have a doubt why we are comparing these two different molecules.
No, this is another way of writing. So I'm just saying, for water molecule, we picked up the elements. This is x-axis, y-axis, z-axis, and then we wrote it. This is one representation, this is another representation, this is another one. Here I'm just adding up the diagonal elements. Here also we can add it. For water molecule, you can add it also. So this is water E. C2 was what? C2 was minus 1, 0, 0, 0, minus 1, 0, 0, 0, 1, right? So water molecule C2 was 3 by 3, so you can add it up here.
So, but my doubt was why we are writing the character table of one molecule and reducible representation of another molecule together.
Oh, both the molecules have.
We do? Point group is same. Point group is same, but the reducible representation will be different, right?
Yes, the representation can be
the
different.
Character table will
different molecules. So point group is same, so we are applying both. So water molecule, your question is water molecule, we can write this one, right?
Yes.
So I'm saying this is for cis-butadiene, you can say butadiene. And the representation for water you can write. So this is E is 0, 3, and for C2 it is minus 1, and sigma V prime. What was the matrix? Remember, it's 1, 0, 0, 0, minus 1, 0, 0, 0, 1. So we should add the diagonal elements. So it is 2 minus 1, it's 1. So I write it here. 3. This is -1. Again, this is 1. And sigma b double prime for water is -1 0 0 0 1 0 0 0 1. Okay, if you add it up again, it is 1 here. Okay, so diagonally if you add it. So 1. So for water molecule, if you add the diagonal elements, so this is a representation. For E it is 3, for C2 it is -1, for sigma b prime it is 1, and sigma b double prime it is 1. But if you write in this form, no, if you add it up, no, it's a mix of all the characters. It could be add of a mix of X, Y, Z. So we don't know this 3 corresponds to what. Okay. So this we call it reducible representation. So if you add the diagonal elements and write it in the character table, we call that as a reducible representation. And if you just pick up the row wise and then write it in this form, then we call it as irreducible representation. Okay, so for x-axis we took it, so it's 1 minus 1, 1 minus 1. So that is irreducible representation, and we know what is the character of, what is the basis for it. For x basis, it is these are the characters. For y basis, it's 1 minus 1 minus 1 1, and z basis it is 1 1 1 1, all symmetric. But when you add the matrix diagonal elements, find the rank, and then find the trace of it, and then write it in the scatter table. So this is called as irreducible. This is called as reducible representation. So there are ways to go from this to this. So after writing, we go to the irreducible representation. Yes, yeah.
So are not we going to write the fourth reducible representation also? Because irreducible representation. Fourth irreducible representation.
We are going to write. So this is a reducible representation. So these two are reducible representation. Reducible representation. Whereas the first 3 are irreducible. Let me switch on. So these two are reducible, and these 3 are irreducible. So we'll see how to go from here to here. Okay. So that's our next objective. Before that, yeah. Okay. So now you got to know how to write the reducible representation. You take up the molecule, either the Cartesian coordinate or the orbital shapes, and then apply these operations, CE, C2, sigma v prime, double prime, and then write in a matrix form. If you sum it up, the diagonal elements, then you'll end up with reducible representation. Okay. Now there are ways to go from reducible to irreducible representation. Shortly, we're going to see that.
Excuse me, sir.
Yes.
I said the dimension of the matrix will depend on the basis only.
Dimension of the matrix depend on basis only. Yes. Yeah. Yes.
Okay. Okay.
Yes, it depends on the basis only. If it is 4 by 4, here it is Butadiene is 4 by 4, right? So that is the dimension is 4 by 4, and then if you take the Cartesian coordinates, it's only 3, right? X, Y, Z could possible. So that's what we got for water molecule. So the matrix form is only 3 by 3. If you take say benzene molecule, you will have 6 representation. You will have all pi orbitals, right? So here you will get 6 by 6 matrix. So the dimension, reducible representation dimension will be is going with 6. It will start from 6. If you are looking for benzene, and then say if you are considering each atom, and then for each atom that could be X, Y, Z. Say in water itself, we can consider water in that 3 atoms are there, oxygen and 2 hydrogen. For oxygen, that could be X1, Y1, Z1, and hydrogen it could be X2, Y2, Z2, and second hydrogen it could be X3, Y3, Z3, right? So that means the basis we have to take a bigger basis. So we call it as a H1, this is H2. Okay, so I can write this one as X1, Y1, and then Z1. The oxygen atom itself, I can say X1, Y1, Z1. And then I consider this as spherical. This is X2, Y2, Z2. For hydrogen atom, 1, I can give it as 3 Cartesian coordinates. And then for hydrogen atom 2, again, that could be 3 Cartesian coordinates, X3, Y3, and Z3. So if you consider this as a basis, then you will get 9 by 9 matrix. Okay, so instead of just 3 by 3 matrix, here we are taking whole molecule is only having XYZ coordinate. So we got 3 by 3 matrix. That's why the matrix representation was, if you sum up the diagonal elements, it was like this. Now if you consider each element has 3 coordinates and then write the basis, then it will be 9 by 9 matrix. Okay, so the matrix depends on the basis we are taking. Okay, so I don't want anything. I just want to consider these 2 bonds. Simple. I want to know only about the symmetry of vibration of these 2 bonds. I call R1 and R2. If I just consider only these 2 representation as a basis, the bonds between these two bonds, I call it as R1 and R2, and then you will get 2 by 2 representation. Basis is R1 and R2, so 2 by 2 matrix. So basis is, the basis is R1 and R2, and your matrix is 2 by 2 matrix. Simple, that's it. So it depends on the basis we are considering. The representation, the matrix form will be depending on the basis. Okay, I think I tried to answer. And then notation now. So now we are writing gamma 1, gamma 2, gamma 3 for various characters. Let's go to another notation. It's called as Mulliken notation. To further classify or just simplify the representation, Mulliken has given certain representation or there's some system to follow. Let's go to that.
Sir?
Yes.
Sir, there is one irreducible representation is missing. There should be 4 irreducible representation, right? Because irreducible representation is equal to number of classes. And we have 4 classes and 3 irreducible representations.
Yes, I agree. So this is not complete. What I have written for water molecule is not complete. There is gamma 4 also. Okay. So gamma 4 will have one more. So you got 1 here plus to 1 minus 1 minus 1 will have. Okay. So for water molecule, there will be 4 IRs. Okay. So you can be gamma 1, gamma 2, gamma 3, gamma 4. Gamma 4 will have factors of 1, plus 1, minus 1, minus 1. And this will be blank here. Since we have considered only XYZ Cartesian coordinates, we could fill only gamma 1, gamma 2, gamma 3. Okay. Since we are not considering anything else, this did not come. But if you consider rotation, say water molecule is rotating. So water molecule is rotating. The oxygen is, say oxygen through this one, through oxygen, and the molecule is rotating. Continuously, if it rotates along this direction, or it can rotate in, say this is rotating like this, or it can rotate tumble also, right? It can tumble also like this, or it can rotate like this. So if you consider those rotations, you will get in a carrier table, there will be one more column for rotational basis. So that is for gamma 4, it will have rotational basis. We call it as R. Rotational basis given by symbol R, and that will have. You can give that. RZ. That is RZ. Basically, whatever basis we are taking, Z-axis, it will have that symmetry. Is it visible? RZ I am writing. Is it visible or not to you? Maybe not, right? So,
no, sir.
It's not visible. I think I'll rewrite it, this one, with proper notation. But time being, just consider with basis based on XYZ Cartesian coordinates, we'll get only 3, gamma 1, gamma 2, gamma 3. But if you consider rotational motion of the water molecule, then you will have the 4th one also. This one, gamma 4, which will have the factors of 1 plus 1, minus 1, minus 1, because there are 4 classes in water molecule. Okay, it's every element is classed by itself in water molecule. So because of that, there should be 4 gammas. Fourth gamma comes in by considering the rotational motion of the water molecule, which we did not consider when we study the XYZ Cartesian coordinates. Okay, the fourth one will also come. Okay, did I answer your question? I think Robin asked, someone asked.
Yes, sir.
Yeah, so that is the rotational motion. If you consider, it will come. Okay, I will write that shortly. Before that, I will introduce the Mulliken notation. For representations. So say if the matrix of the or the IRs, irreducible representation are one dimension. Okay, so it is given by A or B. Symbol A or B is given. If it is 2 dimension, it is given symbol E. If it is 3 dimension, the symbol is given T. Okay, so that's the first rule. If the IRs you have no, so if it is they are of various dimension. If it is 1 dimension, it could be A or B. If it is 2 dimension, it's E. 3 dimension, it is T. Second is how do you like considering the 1 dimension? If the IR is symmetric with respect to principal axis of rotation, then it is given a symbol A. So if its IR is symmetric, with respect to principal rotational axis. Then it is A. So basically, symmetric means chi of 1. Of the character of C2 will be +1. Then it is given A. If it is antisymmetric, chi of -1. It's a character. Chi means the character of each element, each IR. So these are various characters. Okay. So if you consider the character of each IR, and if it is antisymmetric, it is negative with respect to rotational axis. With respect to rotational, then symbol is given as B. Okay, so this is the second property. So you have 3 types: A or B, E and E, E and T. And if it is symmetric with respect to principal rotation, it is A. Antisymmetric with respect to rotation, it is B. Okay, so third is so if it is symmetric with respect to all the operations, it's very simple. Symmetric with respect to. Okay, so this I can write it later, I think. If there are many A's or B, if many A's or B's are present, then you use a term called A1, A2, A3, so on, or B1, B2, B3, so on. Okay, so this is the third one. If there are many A's. So fourth is if the molecule has I symbol, if the point group has I, the inversion symmetry, then it is the A's or B's are given as either G or AU, or like BG or BU or EG or EU, again TG or TU. Okay, so G means Garayed, right? So it's symmetric. If it is symmetric, if the molecule has I, that means it has a symmetric nature. So you can write AG or BG. B comes from the antisymmetric property of rotation. E is two-dimensional character, T is three-dimensional character. And then if they are symmetric with respect to I, then it is G. If it is not, it is given by U. So G is Garrett, U is ungarrett. So this is fourth. And last one is maybe you can say this is prime is also used. If there are multiple A's and if the molecule has sigma H plane. Okay, so if the molecule has sigma H plane, the molecule has sigma H, and if it is symmetric with respect to sigma H, then A prime is given. Okay, and if it is antisymmetric, with respect to sigma H, then A, I think A double prime is given. Okay, so these are the various notations we use. Bath notation is a common one. They don't identify what is what, so they just write gamma 1, gamma 2, gamma 3, gamma 4. But Mulliken representation tells about the characters present in the C2V point group. So I'm going to write that and stop it. So it has a 4 class. It's all our class by itself. So 4 class, you can say. If you write that 4 class, it is. So this is you can say this is XZ, and this is YZ. So XZ means we are just cutting the molecule into half, the water molecule, and YZ means just we are slicing the molecule. Okay. So A1 means all symmetric 1, 1, 1, 1. So this will be having Z character. The basis will be Z, where these characters are representations A1, and it will have A2. Again, A2 means it will be 1, 1. Both are symmetric with respect to A2. So this will be minus 1, minus 1. Nothing will be there. This will be RZ. The rotational mode will be Z type. Then there is a B1. B1 is B means it's negative here with respect to C2, and then sigma V is again positive. Sigma V prime is negative. Okay, so B1 is it will have X character, and if you see the rotational, it will be RY. We'll come to this last one later, but yeah. So the last row for 4th class is B2. So it is 1. Minus 1, minus 1, again plus 1, y is easy. So y should be here, and this will be Rx. So you can write something like this. Okay, so this is the character table for water molecule. Partially I have written. There is one more column, but I didn't write that. But this is the character table for water molecule. So what is character table? Character table is which contains various symmetry operations and its characters in a table. It's called as a character table, or technically it is a table listing all irreducible representations of a point group. For C2V, there are 4 point groups: A1, A2, B1, B2. So it's a table representing all the IRs present and the characters with respect to each IR. And along with the basis. So these are the bases. So the Z basis, X basis, Y basis, or rotational basis. Rx, Ry, Rz. These are the bases. For the basis, these are the IRs and corresponding characters are written. That is called as a character table. Okay, so with the notation, I mean, there is a Mulliken notation. So you can say this A1, A2. So it has 4 elements, right? There are 4 classes. That means when you perform the similar transformation, you'll end up with four classes. So that's what we got. And then the A1, A2, B1, B2. There are multiple A's, that's why it's A1, A2. There are multiple B's, that's why it's B1, B2. And then why B? Because it's antisymmetry with respect to C2. You can see under C2, there are 2 negatives. That's why it's negative. And we didn't use prime because there is no sigma H plane in this. Okay. I'll stop it here. I think you have a class, I think, right? 3 o'clock. So maybe we'll start. Maybe I'll address your questions maybe next class. Okay. You guys go through it, and then we'll discuss with your queries. We'll start the class with answering your queries. Okay. Because this table we'll use it for future classes. Okay, I'm going to stop this presentation or recording. Okay, yeah, see you. It's done.